All right, recording has started. So good morning, everybody, and welcome back to Math 115. We're really kind of approaching the end of the semester here. And let's see, what did I want to say? Well, I guess I have good news. The good news is I'm finding myself actually sort of ahead of where I was supposed to be by now. I followed the schedule pretty much to a T. But it turns out that like the last couple things are sort of that we want to learn are sort of negotiable. So I am gonna sort of deviate maybe a little bit from the syllabus and just sort of maybe do a couple of lectures that are a bit more mathematically interesting. We'll see. But in any case, we're pretty much very, very close to done. In fact, once we finish this, right triangle trigonometry, we might do a little bit of geometry or a little bit of some other fun stuff, and then we'll be done. So we're getting very close to the end. And before I start, let me address a question that just came up in the chat, which is the question, is my grade on Blackboard my actual grade? And the answer to this question is no, it's not. In fact, I included a statement about this on the syllabus. So let me go back and open that really quickly. This was the relevant section. Okay, so the section says, I will upload your raw scores and exams and assignments to Blackboard. Blackboard will give you a total points / earned divided by total points possible score that does not reflect your actual grade. Since the grade for our courses are heavily weighted towards exams, it's not very reasonable to try to compute your grade using just the Blackboard before you've actually had the other components of your grade. So this is how you can actually evaluate your grade. What you need to do is the following. This is the grade breakdown, okay? So homework, exit slips, exam 1, 2, 3, and the cumulative final. Okay, so what you should do is the following. 0.2, okay, so that's for 20%, times your average homework score out of 100. And then 0.07 times number of completed exit slips. Exit slips divided by the number of possible. And this is a plus. And then plus 0.16 times your exam 1 score, plus 0.16 times your exam 2 score, plus 0.16 times your exam 3 score. And as soon as I finish grading the exam 3, pretty much all of this will be determined. And if you want, what you can do is solve this algebraic equation, plus 0.25 times x equals your desired grade. Okay. So if you want to get like an 80 or whatever, then say if I had an average of 0.9 on my homeworks, I put 0.9 here. I say I did 80% of the exit slips, I put 0.8. I got a 90% on exam 1 and 80% on exam 2 and 90% on exam 3. I'd multiply all this stuff out, and I'd get some number plus 0.25x is equal to, and then say I wanted to get a b, I'd put a 0.8 on this side, and I'd solve for x, and that would give me what I should get on the final in order to get an 80. So that's how you can compute your grade. If this seems too complicated to you, that's fine. Just come to office hours, and I will go through this entire process with you and evaluate what you need to do on the final in order to get the grade that you want. So just come and talk to me in office hours if you want like a really, really good understanding of your grade where I compute all of this stuff for you. I'll do that for you in office hours, but it's just too time consuming for me to make Blackboard do this. In fact, it's practically impossible for me to make Blackboard do this right. So I'm going to rely on everyone in this class's algebra skills to figure out how to compute your grade using this simple process. So if you have trouble making this work, just come and see me and we'll talk it over in office hours. Okay, have I fully addressed your question, Catherine? Okay, good. Does any other student in the class have questions about how the grade will be calculated? Okay. If not, this is not what I need. What is that? Oh, this is what I need. See week 14, Tuesday, YouTube video. Okay, so that's addressing that question. All right. So let me remind us what we were talking about last time. So we were talking about right triangles generally, and we were talking about, well, the principle of how I do trigonometry using the unit circle is really sort of a special case of what we call right triangle trigonometry. Okay, so right triangle trigonometry is to say, well, we have a function which is going to relate any angle theta which is inside of a right triangle to the side lengths of that triangle. Okay, and we're going to see in a little while what those relationships are. Okay, if you've seen Sohcahtoa before, that's where we're going. So in other words, basically we're just kind of expanding our frame of reference from not necessarily a triangle which is inscribed inside the unit circle, but our triangle could really be much larger. Okay, so the nice thing about triangles which were inscribed in the unit circle, such as this blue one here, which maybe I'll highlight in green, this triangle here was very convenient to work with because since it was inside of the unit circle, the hypotenuse, we knew that the length of the hypotenuse was 1. Okay, so now we're going to expand our knowledge to other right triangles whose hypotenuse might not necessarily have length 1. But the interesting thing about these two triangles, being the green triangle, which is highlighted, and the pink triangle, which is much larger, is that they are similar triangles. Okay, so these similar triangles have the same angle measurements on the inside. Okay, same angle measurements in the same places. And the side lengths, well, the side lengths won't be the same, but they will be proportional, which is to say that if we take a look at the side length, which was on the up and down side, like this y here, then y and b will be proportional to another side of the triangle, such as this hypotenuse, which y divided by the hypotenuse of the smaller triangle. So the side length of the smaller triangle divided by the hypotenuse of the smaller triangle will have the same ratio as the ratio between the side length of the larger triangle and the hypotenuse of the larger triangle. So since we defined sine of theta to be this guy on the right, another way to define sine theta would be to define it as this ratio between the two side lengths of this triangle, where this triangle doesn't necessarily have to be inside the unit circle. Okay, Om Kumar, just email me about that issue, and I'll look into it. So just email me and let me know which homework it is, and I'll check that for you. Yeah, please do make sure that you check your grades on Blackboard and make sure that they match up with what you see on My Math Lab. Okay, because when I enter those grades, I have to like go through manually and look at the thing, and I'm transferring them over from My Math Lab onto Blackboard. So sometimes I make a numerical mistake. So if I make a mistake, please do check it and make sure, and I'll go back and fix that for you. Okay. So the other thing we talked about was that the side lengths of a right triangle obey the Pythagorean theorem, okay, which is to say that we have the sum of the squares of the two side lengths, which are not the hypotenuse, will be equal to the square of the hypotenuse, right? A squared plus b squared is equal to c squared. I think you guys have probably seen that since like 7th grade or something. And a Pythagorean triple was the name which we have for a collection of 3 integers. Okay, so whole numbers. 3 integers which satisfy the Pythagorean theorem. Okay, so the most famous example of this is the triple 3, 4, 5. Has the property that 3 squared plus 4 squared, well, that's 9 plus 16, and 9 plus 16 is 25, and that's 5 squared. So this is the most famous Pythagorean triple, but there are others. And that was the exercise we did right at the end, was to find other Pythagorean triples. I think the second most famous one is 5, 12, 13. That's another Pythagorean triple. So if you do 5 squared plus 12 squared, that's 25 plus 144, which is equal to 169, and that is equal to 13 squared. So that's another nice collection of 3 like integers which satisfy the Pythagorean theorem. But also any scalar multiple of the triple 3, 4, 5 will also satisfy this equation. So a triple of the form 3n, 4n, 5n, where n is any integer, this will satisfy, well, n is not an integer, n should be a natural number. So one, 2, 3, 4, ... but no negative numbers, right? Because we can't have negative side lengths. Okay, so any scalar multiple of that, like 6, 8, 10, or 30, 40, 50, or 300, 400, and 500, stuff like that, will also satisfy the Pythagorean theorem, and it will be a Pythagorean triple. Okay, so this is really more like trivia than anything else. So if you really like, thinking about this sort of thing and wondering, well, how could I arrange numbers as the side lengths of, the side lengths of this triangle, such that this equation a squared plus b squared equals c squared is satisfied, and a, b, and c are integers? Well, you might have a sort of burgeoning interest in the field of what we call number theory. So number theory is all about understanding numbers and how numbers, can add up to one another. And so there's all sorts of different equations, such as the Pythagorean equation, that number theorists study, and they want to know what kind of solutions they have and what sorts of numbers work with them, and what are the interesting properties of numbers. So that's what number theorists do, among other things. Okay, and that got me thinking that I'd kind of like to take a quick detour and talk really quickly about mathematical notation and set theory. And I'm really struggling to remember, but I think that we started this semester talking about some set theory. I swear we did some like intersection and union. Am I crazy? Did we do intersection and union? We did. Okay. Yeah, we talked a little bit about sets. Yeah, okay, here we go. Yeah, we did intersection and union. I'm going to return to this and talk a little bit more about this. Okay, because this is really important, and I feel like it could bear a little bit more discussion. Okay, so let's define what a set is. A set is a collection of numbers. Well, a collection of items, usually numbers, but possibly other sets or something like that. So a set is a collection of items, usually numbers. We usually denote S to be our set. And we use these squiggly brackets, which I'm awful at drawing. Maybe I'll make a good one. Yeah, I'm not one of those math professors or math instructors who can do really good squigglies. Okay, we use these squigglies, and then inside we list the elements. So, for example, one set that we could have would be the set of numbers 3, 6, and 12. Okay, so this is a set of numbers, and it is the collection of numbers whose value is either 3, 6, or 12. Okay, so there are 3 elements in the set. Three elements in the set. And each element is, well, 12 is one element. Element of the set. Okay, so an element is just one item from the set. Okay, so we have a collection of elements, and these form a set. Okay. We can define a set in a couple of ways. The first way number 1, is to list all of the elements. Like we did up here. We can just list all of the elements. And this works when the number of elements is very small. Okay, this works when the number of elements is very small. By the way, stop me at any time if this stuff is confusing, because I know that set theory is a bit more abstract. Okay, so if you start getting confused about set theory, just pause, type something out in the chat, and ask me to go back and explain further. Okay, so far our set is basically like a bucket, and inside of our bucket we throw some numbers, and we call the set the bucket with the numbers in it, and we call each number which is inside the bucket an element of the set. Okay, and so if we want to describe a set, we can do it in a couple of ways. So the first way is we can just list all the elements. We can say the set S contains the numbers 3, 6, and 12. It's a very simple way of defining the set. And it works nicely if there's only 3 elements. We can just say what they are. But it's not as useful if we have, say, 600 elements in our set. Okay, 600 elements in our set. Or infinite elements in our set. So sometimes we use set notation. Or there's a special word for this, which I don't remember what it is. Crap. Maybe it is set notation. Okay, we're going to call it set notation, which is to do basically the following. You say S, okay, our set is going to be equal to X such that. So this ST means such that X is a number which is less than or equal to 10 and larger than or equal to 0. Then this set contains infinitely many numbers okay. It contains the numbers like 0, 1, 1.5, pi, e, 1 over 1,000, all sorts of these numbers, okay, are in this set. As long as the number has a value or decimal expansion, which is smaller than 10 and larger than or equal to 0, then it's in the set. Okay, so this is an example of a set which contains infinitely many numbers. Okay. So this is just sort of review. I think we kind of talked a little bit about this at the start of the class. But what I want to tell you guys about now is a special set. Well, I want to tell you about 4 or 5 special sets of numbers, which you might have learned about previously. Oh, one more thing before I get to that, which is notation. We write the following. X, we do this sign that looks like a E kind of looking thing. When we write this, we mean is an element of. Okay, so this E looking thing, or like a backwards 3, okay, this means is in. Okay, is in. So if X is in S, for example, for this set where S was the set, so if S is equal to 3, 6, 12, maybe 3, 6, 12, then we might write that 3 is in S, or 6 is in S, or 12 is in S. Okay, so that's just notation. If you go on further with math, you'll see that all the time. All right, so that's just a piece of notation. And the special sets of numbers that I want to discuss are the fundamental sets of numbers, which we kind of use on a regular basis and are useful to set us apart from one another. The first special set of numbers is the natural numbers. We already talked about the natural numbers a little bit. In fact, I asked you guys whether you guys thought that 0 was a natural number. My personal opinion, and this is 100% feeling and 0% actual mathematical justification, is that 0 is not a natural number, just because I feel like it's highly unnatural. So these are numbers like 1, 2, 3, 4, ... to infinity and beyond. Okay, so the set of natural numbers is this set of numbers which are whole numbers and positive. Okay, so no fractions, no decimals, no negatives, and no 0. That's how we define the natural numbers. And we use a special symbol to describe it. We draw one of these n's and we put a little thing here on the side like this. So a double line on the left side of this n. So that means natural numbers. Okay. All right, let me ask you guys, what other sets of numbers have you guys heard of besides the natural numbers? We talk about the natural numbers a lot in this class. Has anybody heard of any other sets, famous sets of numbers? No other famous sets of numbers out there besides the natural numbers? Ah, there we go. Heidi's got one. Aeon's got one as well. And Catherine's got one too, although she doesn't know the name of it just yet. There is one that includes 0. Sometimes people call that the whole numbers. And let me just preface this. This one is controversial. The whole numbers are 0, 1, 2, 3. In other words, well, ... In other words, this set is equal to the natural numbers union 0. So we take the union of the natural numbers with the set 0. So that's the whole numbers. So thanks, Catherine, for reminding me of their existence. And then there are a few others that came in into the chat, such as the integers. I think that's the next one. And the integers are basically all whole numbers and 0 and possibly negative numbers. So ... -3, -2, -1, 0, 1, 2, 3, ... And the letter we use for these guys is a Z. And we do another one of these lines in here. Okay, so those are the integers. So a number is an integer if it is a whole number, but possibly negative. And by whole number, I don't necessarily mean this whole. I just mean in the general like linguistic sense of the word whole, it's a non-fractional number, non-decimal number. Okay, and then there was another one which was given, and I'm going to leave some space because there's actually a fourth set of numbers which I want to talk about before I get to the reals. Does anybody know what should go before we talk about the reals? Something which is somehow in between an integer and a real number. Real numbers can be very nasty, can be things like pi or e, or infinitely repeating decimals. Aha, that's the word I'm looking for, rational numbers. And rational numbers are defined in the following way. X is equal to AB such that A is an integer and B is an integer. Okay, so the way to read this notation that I just wrote down is that X is equal to the ratio of A to B. That's why we call them the ratio null numbers, rational numbers. And this such that just means that we're now going to list the rules that A and B must satisfy. Okay, and we say that A has to be in Z, which means that A has to be a number like -3, -2, -1, 0, 1, 2, 3, dot, dot, dot. And B should also be an integer. Okay, so this is basically things like fractions where the numerator and denominator are both an integer. So, for example, and by the way, we write Q for this one with a thing. So for example, numbers like 1/3 or -10 over 6, 6, 6, 6, 6, 6 is also a rational number, or also 0 or 3, right? Because we can take the denominator to be 1 if we want. Okay, so these are rational numbers. So the numerator has to be an integer and the denominator has to be an integer. And in fact, I should say that b is in Z and b is not equal to 0. So these are what we call the rational numbers. We call them the rational numbers because they come from a ratio of integers. Okay, and then the real numbers is Q union. I don't even remember what we used for the irrational numbers. I think it's I. Simple. Let's Google it. I disagree with all of these. Okay. Oh, Q primes, okay. Well, okay. I'm just going to write irrational numbers. So X could be, and by the way, we use the big capital R with the double line. So we take all of the rational numbers and then we add to that set all of the possible irrational numbers. So irrational numbers could be numbers like pi or e, or we could have rational numbers like 1/3, or we could have 0, 1, -1, whatever. Basically any number that you can think of that's not part of the final group of numbers, which is complex numbers. Okay, so real numbers are all numbers which don't include any imaginary component. Okay. So we could also have in here things like the square root of 2 or the square root of 5. Those are also real numbers. Or the negative of those two would also be fine. Okay, and so finally we have the complex numbers. The complex numbers are basically the real numbers. No. The complex numbers are the following. X is equal to A plus B times I, so that A and B, A is a real number, B is a real number, and I is equal to the square root of -1. And this is probably the most complicated numbers that most students in this class will ever see. Okay, so we have this number, this letter I, which we use to denote the square root of -1, which up until just now has not been defined in this class. But you can define it in this way, and you can say A plus BI is A, the real number, plus B times this imaginary unit I, which is the square root of -1. Okay, and you can do all sorts of interesting math using these complex numbers. Sometimes these are called imaginary numbers. And it's sort of a misnomer, because complex numbers, although they might seem like, well, it doesn't even make sense, they don't even exist, they're imaginary, they're very much in existence, and they're very much motivated by the natural world. In fact, the ordinary differential equations which we use to describe pretty much every physical process that has ever existed in our universe are intimately dependent on the understanding of complex and imaginary numbers. Okay, so for example, the mathematics which is behind the production of the images which are on your computer screen right now, for example, is completely reliant on the fast Fourier transform, which is a process which involves integration using imaginary numbers. Okay, so imaginary numbers, although they may seem like, well, it's imaginary, so like, who cares? We do care about imaginary numbers. They're extremely important. Okay, but we're not really going to talk that much about them. I'm just going to tell you that they exist and they're important. Okay, so these are all of the different types of numbers and the symbols that we have for them. And remember, all of these symbols are representing a set of numbers. Okay, so if I write something like X is in Q, what I mean is X is a rational number. Or if I write X is in, oh, by the way, the symbol for the complex numbers is, of course, a C with a little line. If I write X in R, then I mean X is a real number. And so on and so forth. Okay, so this is some kind of fun review about how we call numbers, okay? So if a number is like a fraction, we're probably going to call that number a rational number. If it's, irrational, then it'll be a real number, or you could call it an irrational number. And then, complex numbers also exist. Integers and natural numbers. The only one that's really, I've never really seen too much of is the whole numbers. So don't forget that that one's sort of controversial. Some people believe that 0 should be a natural number. I personally don't. That's just my opinion. Okay. So I just wanted to really briefly touch on this because this is something important, especially if you're going to move forward with math. Being familiar with these basic sets of numbers and how we kind of define these numbers is useful, quite useful. Okay. So any questions on sets of numbers or these 6 famous kind of types of numbers? Questions or comments, I guess. Why do we use complex numbers? Well, I could probably give a semester-long class on the uses of complex numbers, but in fact, you could give several semester-long classes on complex numbers and why they're useful, or the places where they show up. But basically, okay, this is hard to describe, but basically, there are these things called differential equations. Okay, so differential equations are equations. Okay, we haven't even talked about derivatives. There are things called differential equations, and differential equations are used to model motion. So basically, everything in physics, or for example, heat transfer, or the motion of waves, either electromagnetic waves or literal waves like in the ocean, or longitudinal waves such as sound, right? So we have differential equations which we use to describe these physical processes. And invariably, the physical process involves a computation. Modeling the physical process involves a computation which uses complex numbers. Okay, so we have something which is called the complex plane, which the complex plane is basically the real axis versus the imaginary axis. And you can basically model differential equations in this plane, and you can look at the way that the trajectories work, such as if we have like a circle motion, then this could model something such as like planetary motion around the sun, right? You can have, or you could have like an elliptical trajectory of something which is, moving around the sun in an elliptical way. So you can describe planetary motion using imaginary numbers. You can describe, for example, how heat transfers if you have like a steel rod, right? And you have that it's, very hot here in the middle, and then, less hot on the sides, and relatively cool on the ends. You can describe how this heat is going to basically radiate out through the substance using differential equations, which also involve imaginary numbers, and also basically everything that we know about electricity and magnetism is also completely contingent on complex numbers. But I think actually defining what is going on with all these things in a rigorous way is really kind of beyond the scope of this class. But if you want to learn more about that, it's a fascinating thing to talk about. So you should take more math classes and you'll learn even more about this stuff. So that's the short answer to your question, Kumar. Okay. Well, I'm going to get back off of my tangent and off of my soapbox and return to our discussion of trigonometry now. So for the last bit of class here, we'll talk about trig. So before we talk about Sohcahtoa, we need to talk about the definition of hypotenuse, opposite, and adjacent legs. Okay, so we use the following terminology. If we have specified an angle theta, okay, if we've specified an angle theta, then we call the leg of the triangle which is right next to theta, but isn't the hypotenuse, okay, isn't the hypotenuse. We call that the adjacent leg. Okay, so adjacent just means next to. If I'm sitting adjacent to you, then I'm sitting right next to you. So this is the adjacent leg as opposed to the opposite leg. Now the opposite leg is the leg which, if we start at the angle and we go straight across, we get to this leg over here, and we call that the opposite leg. Okay, so the opposite leg is the leg which is opposite of our angle. And then the adjacent leg is the leg which is next to our angle. And then the hypotenuse is always the one which is across from the 90-degree angle. Okay, so that's the hypotenuse. So if we have an angle, the one that's next to it, which is not the hypotenuse, we call the adjacent leg, and the other leg, which is across from it, we call it the opposite leg. Okay, and the most important thing to remember about these is the first letter of each word. Okay, so for the opposite leg, we're going to use the letter O. For the hypotenuse, we're going to use the letter H. And for the adjacent leg, we're going to use the letter A. Okay, then the trigonometric functions can be defined in the following way. So here's the first three. We have that sine of theta will be the length of the opposite leg divided by the length of the hypotenuse. Okay, the length of the opposite leg divided by the length of the hypotenuse. So when we're inside the unit circle, the opposite leg is the height of the point on the unit circle, and the hypotenuse is 1. So it's just y over 1 when we're in the unit circle. But in some cases, our hypotenuse might not necessarily have length 1, and we can define sine of theta as the ratio between these side lengths. Okay, so this is going back to that similar triangle idea where we had that the opposite over the hypotenuse will be proportional to that y over 1 value. Okay, then cosine of theta is defined to be the length of the adjacent leg divided by the length of the hypotenuse. And then tangent of theta is defined to be the length of the opposite leg divided by the length of the adjacent leg. And the mnemonic device we have for remembering this is the so-called Sohcahtoa, right? So Sohcahtoa. So the SOH stands for sine is equal to opposite over hypotenuse. The CAH stands for cosine is equal to adjacent over hypotenuse. And tangent is equal to the opposite over the adjacent. So these are this is the meaning of these letters. Omkamarka says he's going to take more math classes to find out about complex numbers. Good. Okay, and then the other ones are just the reverse of those, right? So cosecant of theta is going to be the reciprocal of the sine, and secant theta is going to be the reciprocal of cosine, and then cotangent is going to be the reciprocal of tangent, as usual. Okay, and we have all sorts of ways and mnemonic devices for remembering Sohcahtoa. So these are two of my favorites. So you can always remember that some old hippie caught a high tripping on acid, or you can remember some old hag cracked all her teeth on asparagus. And there's like a billion more, by the way. So if you learned another one in high school, I'd be really curious to hear what you learned. There are some other ones involving math classes which are not as fun, I think, as these ones. But these are some ways that you can remember the mnemonic device. Okay, Aeon's got another one involving acid. It says some old hippie caught another hippie tripping on acid. Yeah, caught another hippie. Yeah, that would work too. So you could also use another hippie. Although I'm not sure that that one makes much logical sense, because that would imply that like it's somehow like, you know, the first hippie would be upset that the other hippie was on acid. I don't know. Okay, cool. Yeah, so that's a way that you can remember this stuff. He wanted him to share. Yeah, maybe. So, okay, so that's how you can remember Sohcahtoa. That's just kind of a fun thing. All right. So let's see how this actually works in practice. So I'll help you guys do the first one. So if we want to find out what sine of theta is, and we have this triangle here, this nice right triangle, where we have all the side lengths. Oh, we don't have one of the side lengths. But we can find sine theta relatively easily because we know that sine theta should be equal to the length of the opposite side. So I'm going to use SOH here. Opposite side divided by the length of the hypotenuse. So the opposite side from theta, I start in the corner with theta and I go straight across. And that's how I find the opposite side. So in our case, sine of theta is going to be equal to 2 divided by, well, the length of the hypotenuse is 5. So that's how I can do that. Okay, and then if I want to find cosine theta, well, I can just use CAH. So I know that cosine theta is going to be equal to the length of the adjacent side divided by the length of the hypotenuse. And it looks like our adjacent side is b, and our hypotenuse is 5, so I'll write b over 5. And is there any way that I can know what b is? Any ideas on how we could figure out what b is, the length of this adjacent side? Yeah, we can use the Pythagorean theorem, right? We know that these b and 2 and 5 should all satisfy the equation that b squared plus 2 squared should be equal to 5 squared. So if we just multiply that out, we'd get b squared plus 4 is equal to 25. And therefore, b squared is equal to 25 minus 4 is 21. So then b is the square root of 21, which is completely simplified since 21 factors as 3 times 7, and then neither of those can come out. So I'm going to write square root of 21 here. So that's how I can find cosine of theta. And I might as well fill that in on my thing here. This is the square root of 21. All right, and then the last thing we're supposed to find out is what is tangent of alpha. Now, alpha here is this angle which is in the top corner. So this angle which is in the top corner. So tangent of alpha, oops, will be equal to, well, we use TOA, right? TOA tells us it should be the opposite leg divided by the adjacent leg. So what do you guys think about 2 over 5? Agree or disagree? Well, we don't need to use the Pythagorean theorem anymore since we know what the lengths of all the sides are. Okay, disagree with what part? All of it? Or what do you suggest we should do instead? Mm-hmm. Okay, so the thought is that we should replace the denominator by the square root of 21. Okay, I think that's good because first of all, 5, right, is the length of the hypotenuse. Okay, so 5 is the length of the hypotenuse, so hypotenuse isn't anywhere in our formula here, so we should definitely not use the number 5 in our ratio. What do people think about the ratio 2 over root 21? Have we got it right now? Agree, disagree? Everyone agrees? Okay, well, I'll disagree. I'll say that there's still something that we need to fix here in this formula here. And I'll give you a hint. The hint that I'm going to give you is that the problem is sort of okay, well, yeah, we could rationalize the denominator, but that's not the problem. There's another problem, which is more important than rationalizing the denominator, which is that we're using a different angle now. We're using the angle alpha and not the angle theta. We're using the angle alpha. So if we're using the angle alpha, which leg is opposite of the angle alpha? Yeah, B is going to be the leg which is opposite of alpha. I see where you were going with that now, Sam. I was confused at first. Yeah, B is across from alpha, so B is adjacent to theta, but it is opposite of alpha. And then the 2 is the adjacent of alpha, right? Because the opposite leg is sort of contingent on which angle we're talking about. Okay, so we got to think about what is the angle and which leg is across from that angle. So the opposite leg is the one which is across from our angle, and our angle now is in the top right instead of in the top left. So the side length, which is opposite of our angle, is different. Okay, so in our case, what we need to do is divide the opposite leg, which in our case is square root 21. We need to divide that by the adjacent leg, which in this case is 2. So we should flip this. Flip the script, as it were. Square root 21 divided by 2 is what we should get. And we can erase our question mark. Okay, so what did we see here? We saw that, well, depending on which angle we're talking about, we need to use the correct side lengths, which are opposite and adjacent for that specific angle. Okay, and this makes complete sense because if we draw our triangle out here, we can see that this angle theta is definitely different from this angle alpha. Okay, it looks like alpha is a bigger angle than theta is. So we should not expect their sine and cosine and tangent to take the same values, right? They're going to take different values because they're different angles. So we need to make sure that when we're talking about alpha, we're talking about the opposite. This is opposite of alpha, and this is adjacent of alpha. Whereas if we're talking about theta, okay, then the opposite will be on the other side. So this is opposite of theta and adjacent of theta. Okay, of course, the hypotenuse is always the same for both. Okay, because the hypotenuse is always across from the 90-degree angle. Okay, so that's one pitfall that we have to be a little bit careful about falling into, is that sometimes I think that these problems with the right triangles can get really confusing when the triangle is in sort of a different shape than you've seen it usually be in before, or a different orientation, or when you have to use an angle which is not the angle which we're used to using, which in the unit circle, we always are using this angle which is in here in like the center of the unit circle. But now that we're doing right angle trigonometry, we're going to open that up and we're going to sometimes talk about the angle which is in the top right, okay, which is something completely new. Okay, so what we need to do when we use this completely new angle is to rely on our new definition of what sine and cosine and tangent are, which is the ratio of the length of the opposite leg to the hypotenuse leg, or the ratio of the adjacent to the hypotenuse, or the ratio of the length of the opposite to the length of the adjacent. We need to use this definition, okay? And when our angle is not necessarily in the center, we have to use that definition rather than our old intuition, which is coming from the unit circle. It's good that we have that intuition, but we should use it only when it's applicable. And when we're sitting in this top right corner here, our world is a little bit flipped topsy-turvy. Okay, so we got to rely on our definitions a little bit. Okay, so that's a great way of doing this. Any questions about this problem where we had to find sine theta, cosine theta, and tangent of alpha? No questions. Nice. I really like the GIF response. Yeah. Go ahead and use those all you want. That just really gives me the giggles. Okay, no questions. Then we'll move on to the next problem. I think probably the hardest part of this problem, by the way. Well, first of all, for sine theta and cosine theta, we had to use our new definitions because the length of the hypotenuse wasn't 1. So we had to use our Sohcahtoa. But I think really the hardest part was then to think about the angle alpha, because this is probably the first time we've ever really considered an angle which is not sort of in like the standard position in that bottom left there to figure this stuff out. All right. So now let's try this other problem here. So the next problem, what we're going to try to do is a little bit different. Okay, a little bit different. We're going to try to use some information which we already know about the value of how is this going to work? We're going to use this information which we already know about the value of tangent to say something about the lengths of the sides. Lengths of the sides. Oh yeah, we can solve this for sure. Okay. So we have information about tangent of theta. Okay. So tangent of theta is equal to 3 divided by 4. Okay, so what's the relevant component of Sohcahtoa going to be for this particular problem, do you think? It's the relevant component of Sohcahtoa here. Any thoughts? Well, we have some information given to us, and that information says something about the tangent of an angle, which means that, exactly right, Kamar, we're going to be focusing in on this TOA component. Okay, so TOA says that the tangent of theta is going to be equal to the opposite leg divided by the adjacent leg. So we're given some information not necessarily about the lengths x and y, but about the ratio between x and y. We're told that this is equal to the ratio between the opposite leg and the adjacent leg, which in terms of our problem is a fraction. And what should the numerator of our fraction be? Well, you're getting way ahead of things there. But yes, you're right. You're too smart for my question. I'm first just asking, well, how can we describe the length of the opposite leg? We should do x, right? And then the length of the adjacent leg. So this is the opposite of theta. And I know I should use x in the numerator of this one because I have theta in here. And theta is clearly visible in this bottom left. So I know that the leg which is opposite theta will be the one which is across from that angle, which is x. And then the adjacent leg will be adjacent to theta will be y. So I have the equation 3 over 4 is equal to x over y. And I claim we have another equation. We have one other equation which also involves x and y besides this one. Can anyone tell me what that equation should be? We have one other equation which we know is true. We know that 3 over 4 is equal to the ratio. Yeah, tangent is equal to sine over cosine. Of course, sine over cosine is, if we just plug that in, we're going to get, again, x over y. There's one other equation that doesn't even involve any trigonometry. That's right. We have the Pythagorean theorem should be satisfied by the legs of this triangle. The sum of the squares of x and y should be equal to the square of the hypotenuse. We should have that x squared plus y squared is equal to 10 squared, which is 100. That's the other equation. Now, we have a system of two equations with two unknowns. We can solve this system of equations using techniques that we learned. I guess we didn't really do systems of equations in this class. I guess that's a prerequisite then. So something you maybe did in algebra in high school or in a 111 or something like that. Okay, so we have two equations with two unknowns. So can somebody tell me one of the techniques that I can use to solve a system of equations? What techniques do we have to solve systems of equations? Yeah, both methods work. However, yeah, I guess both methods would work. Okay, so first of all, we could use elimination, which is to basically manipulate one of the equations until one of the sides looks like has one of the components of the bottom in it, and then we subtract those two equations to solve for one of the variables, and then we back substitute. Or we can use substitution, which is what I think is going to be a little bit easier for this one. And substitution is exactly the method that Aeon was describing here. Okay, so we solve for a single variable in one equation and then plug into the other. And the reason that I want to use this method is that it's very easy for me to solve this top equation for x. Okay, I can solve the top equation for x, and I would get the new system of equations is, well, x is equal to 3 over 4y, and then x squared plus y squared equals 100. And then what I'm going to do is I'm going to take x from here, and I'm going to plug it in for x in here. So I get 3/4 y, that's what x is. I should square that and add it to y squared, and I should get 100. So 9 over 16 y squared plus y squared is equal to 100. So 16 plus 9 is 25. Y squared over 16 is equal to 100. So y squared is equal to 100 times 16 over 25, which is then 4 times 16, which is 64. So then y should be the number 8. And we choose the positive square root because what is y? Y is the length of a side of a triangle. It should be a positive number. So sometimes we would say -8 is not physically meaningful. Okay, so we have y is equal to 8. So let's fill that in on our triangle here. We know y is equal to 8. And we also know that, of course, x is equal to 3/4 of y. So since x is equal to 3/4 of y, this is our back substitution. We just plug 8 in. That just means that x is equal to 3/4 times 8, which is equal to 6. So x was equal to 6. And I believe that is what we were required to find, was just the side lengths, x and y. So it turns out that our triangle here is, in fact, a 6, 8, 10 triangle, which is a Pythagorean triple, because 6, 8, 10 is a multiple of 3, 4, 5. Okay, so this is a Pythagorean triple we're looking at here. So something that I just want to point out is that I think the most naive way to complete or to attempt this problem would be to do the following. Would be to see, okay, well, we have tangent of theta is 3 divided by 4. I know that's just the opposite leg divided by the adjacent leg. And therefore, x should be equal to 3 and y should be equal to 4. But you'll find out very quickly that if you were to try to back substitute this into the equation, the Pythagorean theorem, you're going to get that this is not true, right? So 3 over 4 is the simplified ratio of 6 over 8. Okay, so this tangent here is not necessarily going to immediately tell you what those side lengths are. It's going to tell you the ratio of the side lengths, which may be simplified. Okay, so rather than just going and taking this naive approach and saying, well, therefore x is 3 and y is 4, we need to be a little bit more subtle and say, well, we know that from tangent of theta is 3 over 4, we know then that 3 over 4 is equal to x over y. It's the ratio. It may not be the exact values of the side lengths. Okay. Well, I think I'm going to stop here for today. So today was, I think, a bit more fun. Maybe you don't believe it was more fun, but it was more fun for me, anyways, to talk about all this stuff. So hopefully that came through, and I'm going to try to keep you guys a bit more involved, kind of like today, in the next couple lectures, and then we'll be pretty much done. So thanks everybody, and I'll see you guys tomorrow.